Hello, everyone. I'm Yogesh Jaluria from Rutgers University in New Jersey, USA. And it's certainly a pleasure for me to present a paper on some studies that we have done on chemical vapor deposition. The title of the talk is Experimental and Numerical Study of the Effect of Composition on Gallium Nitride Thin Films Grown by Deposition. My co-author is Omar Juma, who was my graduate student and he did most of the work. Gallium nitride and chemical vapor deposition are both important aspects, and that's what we'll be talking about. The applications are shown here. Some of the applications are shown here. Lighting and displays, semiconductors, high-powered RF, and of course, energy automotive composite materials. And these are all related to gallium nitride, as well as some other materials like indium nitride, aluminum nitride, and many others. These are particularly important in recent times because of the interest in LEDs and interest in many other applications that have been arising in the recent years. These are the different kinds of CVD systems. The basic idea is that reactive gases enter at one place, have reactions here because of the heat input at a susceptor, and ultimately deposit the solid material in crystalline form on the surface. Here are some of the other applications, some of the other configurations, and many of these have been used. We've been particularly interested in rotating impingement type, which I'll talk about in a minute. But here is the basic process. The gases come in. This is silane, SiH4, with oxygen coming into a horizontal chamber. There's a reaction and dissociation. Ultimately, the crystal is formed, which is the silicon, which is deposited on a substrate, which is heated. And then, of course, the rest of the material gases are exhausted. The idea is, of course, to get the best quality film. And those films, as I mentioned, are used for LEDs, power amplifiers, many rectifiers, and many other applications. But we also want a very high deposition rate. So our interest is in high deposition rate and high quality film. So those are the two things that we keep in mind. And this is the basic reactor that I'll be talking about most of the time, which is flow coming in into a rotating susceptor. The susceptor rotates at a fairly high speed, typically 300 to 400 RPM, and the flow is largely a laminar flow coming from the top. The equations are generally the standard ones, continuity, momentum, energy, and so on, but a lot of species equations. And then you have source terms and then diffusion, flux, and so on. The chemistry is involved, which you can see from here that the gases are coming in for gallium nitride. You have a lot of reactions going on. These are intermediate reactions. And ultimately, you find that gallium nitride is generated, which is deposited on the substrate, and these gases or whatever is left behind, particularly methane and hydrogen and so on, are exhausted. Looking at all the equations, there are 52 gas reactions and 17 surface reactions. This is often called a full model, but there can be even more intermediate reactions. But if you simplify it, you end up with 17 gas reactions, 17 surface reactions, which is still a lot, and it's a very complicated process to model it. The heat input is needed to make sure that this occurs. At very low temperature, there's not enough energy. At very high temperature, there's too much dissociation. So you have to worry that the temperatures are in the right range. This is an industrial system, about 1.5 meters by 1.5 meters. The flow comes in here at the top and deposits on this rotating susceptor, which is rotating on a spindle right here. And the focus is clearly on this material, on the crystal that is being formed. This is just the setup, a few aspects of it shown. Here there are many wafers on which the deposition occurs. The material may be sapphire, maybe silicon carbide, gallium nitride, whatever, and the crystal is deposited on that. And then it can be a 2D growth, 3D growth, or combined. Our interest lies in a 2D growth, which is uniform and very high in quality. This is the crystal, and then ultimately it is cut in different forms to use for different applications. This is the general structure for gallium nitride or aluminum nitride and many others. And that's what is ultimately used for making electronic circuits, devices, and so on. The numerical model, we picked up this very simple case where it's only a single wafer or single place where a surface, heated surface where deposition is occurring. And we picked it up, developed a model for it, and looked at the results from previous work and some experimental work which had been done earlier, and we compared, and the results were quite close. So we made sure that the grid refinement was adequate. We made sure that the model was correct. And as you can see from this comparison, that it does approximate the results quite well, the experiment result which had been done earlier with respect to this model. The parameters are given here. There were a whole range, different rotating speeds. As you can see, there's very high temperature that you need, velocities, and so on. And we vary parameters to see what is happening. I'll just go through it quickly. The susceptor rotation is very important. As you increase the susceptor rotation, the deposition rate increases, but the standard deviation goes down. So the quality becomes better. The uniformity becomes better. The deposition rate increases. And you can see here that this is at no rotation, and it's very chaotic. At high rotation, it's much better behaved. And you can look at this temperature field also, very chaotic and very nicely behaved at high rotation. So rotation does help a lot in getting the high quality and uniformity that we want. Temperature, as I mentioned, is touchy, because if you have very low temperature, there's very low deposition. If you go to very high temperature, the deposition is also low. You need to be in the right range. And as you can see, that's what is being shown here. And this is the standard deviation, which is pretty much as you might expect, but the uniformity is not bad. And these are the velocities. They don't change very much because of the temperature. There is variable properties, but the effect is not that strong. And this is the temperature field. You can see as you go to a higher temperature, you end up with very uniform and very nice condition here. This is at low temperature. The uniformity is still there, but this is where a lot of deposition is occurring, and you're looking at some very high values of deposition rate. Inlet velocity effect is there. Largely, the effect is relatively small, but you can see that if you make inlet velocity extremely small, it becomes quite chaotic. As you go to higher inlet velocity becomes much better. And that you can see from here, the standard deviation comes down as you increase the velocity. The deposition rate does not change very much, but uniformity becomes better. Reactive pressure, the same thing, that if you have reactive pressure changing, you find that at high pressure, you may get a very high deposition, but the quality is very poor. The quality can be quite poor. Look at this. The standard deviation is very large, so the quality is very poor. And it can also be shown from here, the quality is not up to the standard. And this is the temperature field is also shown here. It's not that apparent in this, but at high temperature, as I mentioned earlier, you can see how bad it could be. Okay. Concentration ratio is interesting because we take ammonia to TMG ratio. Ammonia is given by 5 and TMG by 3. These are the tables, the periodic table columns, 5th and 3rd columns. And so we'll use 5 upon 3. So 5 upon 3 being high means that ammonia is high, but gallium is low. So if you go to very high values, you have very low gallium. So growth rate, as you increase the amount of gallium, you find deposition rate goes up, but the standard deviation also goes up. And similarly here, as you go up in ammonia, you find that the standard deviation becomes lower, but the deposition rate also becomes lower. So the idea that if you make gallium very large, you'll get very large deposition, but the quality is poor. This is with many wafers. Last time we were talking about, earlier we were talking about one wafer. Now there are many wafers. Several wafers are put here. You can use ammonia, hydrogen or nitrogen as the carrier gas. And you can see a big difference. Even between hydrogen and nitrogen, the uniformity is not that heavily affected, but the deposition rate is affected. And this is an experimental result. So it's a reasonable validation from there again. You can look at the pressure again, going up to a higher pressure. Look at this, it starts giving disturbances. So at high pressure, the quality is bad. The deposition rate is higher. So pressure, increase the pressure, deposition rate higher. Increase the concentration, deposition rate higher. But at the same time, your quality becomes down, becomes lower. And you can see this. The quality becomes lower as you increase the pressure. It becomes much worse. Rotation. Rotation generally improves the uniformity. As you can see, it improves the uniformity, and it also increases the deposition rate a little bit, not too much, but the main effect is on the quality. And again, an experimental result comparison. Concentration ratio, as I said, is the most interesting thing, that it increases the deposition. Here, several of them are shown. This is very low gallium. This is very high gallium. This is the worst in uniformity, but the deposition rate is very high. Here, the deposition rate is very low, but the quality is very high. So you can look from here, the same thing is being shown here, that you can end up with good uniformity with respect to high gallium. We have a 5/3 ratio being that means gallium is very small. This means gallium is very high. So very high, good deposition, good rate, but quality is much worse. Because of all that, you can easily see that there's a nice optimum that can be thought of. These are some cases we did on an actual system. This is a control condition, very uniform. But as you increase the pressure, uniformity is lower. 140 to 200 torr, uniformity is lower, but the deposition rate increases by 48%. You go to competition, change the concentration ratio, the flow and everything looks fine, little disturbance, but by and large it looks okay. But again, quality not very good, deposition, but rate of deposition has increased a lot. So that's the challenge that you have. Here's one sample we did on experiment system, on actual physical system. Nice temperature and velocity, both were very nice, very good uniformity. So it shows you that temperature, velocity, they're well maintained, very good uniformity. Measured it by the scanning electron microscope, the difference is only 11%, 11.5% from the prediction, which is much better than what we expected. Similarly, another sample, reasonably good uniformity, and we measure it here looking at the thickness with a profile meter. Again, we see very good uniformity. And with the AFM atomic force micrometer, also we found that it's very uniform. Roughness is less than 0.1 nanometer. So excellent with this particular sample. And the difference was only 4.5% from prediction. Again, very good. Sample 3, same thing. Good uniformity. And again, you got a certain thickness on SEM. Difference is 14.8. So the numerical model and the experiment, even on the practical system, is very good, which made us quite happy. It shows you that the concentration, when it becomes very low, you get very uniform. When concentration is very high of gallium, it's not as uniform as we had seen before. This can be shown RMS value over this ratio. As the ratio becomes high, means gallium is low, you end up with lower RMS, better uniformity. Similarly here, if you increase the ratio, low amount of gallium, your crystal structure with the dislocation are lower. That means the crystal quality is better. So you go to higher value, crystal quality is better. Okay. And also we talked about nitrogen and hydrogen as a carrier gas. With nitrogen, you end up with some contamination. With hydrogen, you end up with much better situation. So hydrogen is by and large the desirable situation. Okay, so by and large, what we have been seeing is, first of all, the model works very well with the experiment. Model compares very well with previous experiments, even with the experiments that we did on lab models, on physical models, on actual practical industrial systems. It works very well. So that's the first thing. The second thing is that most of the things that increase the rate of production or increase the deposition rate affect the quality adversely, which means if you increase the gallium concentration, you get more deposition, but the quality of the crystal is worse. You increase the pressure, again, good deposition, but the quality of the crystal is worse. And same thing happens with inlet, many other situations that you have. Rotation is very good. The rotation increases the deposition rate a little bit, but makes the quality better, uniformity better. So you obviously have an optimal situation. And you can deal with the optimum by looking at these two parameters and doing a multi-objective optimization to get to that. Okay, so I would not get into that because obviously that's a little bit beyond what I was thinking of talking about. But we have done optimization. We have looked at these situations. We also looked at uncertainties and try to see what overall can be done for a practical, reliable system. Okay, to conclude, we are using a combined analytical, experimental, and numerical approach, which is probably the best to obtain results on such a complicated system. We validate by using experiment, by using numerical. The experiment gave us much greater confidence, obviously, than the analytical results or numerical results done earlier. It is important to link the product with operating conditions. And that's why we spent a lot of time on looking at the product, what kind of quality it is. So the numerical modeling gives us an idea as to what will happen, but the product diagnostics is very critical, ultimately to link it with operating conditions. It's critical to optimize. I mentioned that because you can increase the production rate. We always want very high production rate, but at the same time, we want the quality of the crystal to be as high as possible. And the two oppose each other. So it becomes very critical that we try to optimize the system and the process. We did sensitivity analysis just to see if we can simplify the problem, and that helped. I didn't get into it too much, but that helps as to what is important. And we focused on the main parameters. Our focus was on the quality and the production rate. I did not get into the optimization part, but these are the two objectives that we have. Percentage working area, mean deposition rate. Those are the two main objectives. We can make response surfaces, constrained optimization to get it. But I said, as I mentioned, we need to consider uncertainties to make sure design parameters and operating conditions are working properly, because you can have uncertainties in velocity, in inlet velocity, in pressure. How do they affect? Now, many of these things can affect the optimal conditions. We didn't get into some of these for the main reason that I didn't have the time to do that, but I want to bring out that idea that you can do the modeling, you can do the comparisons, and everything is fine. But the next step is optimization, is simulation-based optimization, reliability-based optimization. Much of that we have done. Hopefully, I'll talk about it in some other venue, but that's the kind of direction that we would ultimately need to take to make it into a realistic, practical system. Okay. With that, I think I'll stop. And thank you very much for your attention. Thank you.